don't want your faces to show up on the recording, you can turn your videos off. Though I highly recommend that you leave your videos on in case some recruiter happens to stumble upon my YouTube channel, and then they will get to see this look of concentration and understanding on your face, and then they might hire you on the spot. Rakshit actually fell for that. So no, I'm just joking. I know you're very smart. You're not going to just fall for anything. But seriously, like if you guys could turn your videos on, that is very much appreciated. Okay. Okay. All right. Then somebody is saying, Akash, Wilfred, दे रहा हूँ आकाश, आकाश को दो जल्दी दो. Telegram and Telegram. Acha, it's on the channel. Which channel? Acha, my channel. Oh, okay, cool. Yeah, very people are very like flued in these days, man. Okay, then. Good morning, everybody. Let me start screen sharing. All right, and I'm going to press the record button. No. Okay. All right. So last time I was talking about, in yesterday's class, I was talking about an example of this uncertainty principle. And so I, had made a small sign error in sigma y definition, but then I had like corrected that during class itself. And it turns out that, that correction is right. So if you put a minus sign here and a plus sign here, then the commutation relation works out. Okay. So this is called a commutation relation. The fact that sigma x, sigma y commutator is equal to 2i sigma z and so on. This is called a commutation relation. Now, this uncertainty relationship is correct. It applies to any set of operators. It doesn't matter which operator. In doing this calculation, I had become a little bit confused, but turns out I was doing it correctly. There was nothing wrong with what I was doing. So if you take the uncertainty in sigma z multiplied by delta sigma y, you get expectation value of sigma x and so on. So that's perfectly fine. Okay. And then what was the thing, right? So here there was a little bit of confusion on my part because when I did this calculation of the expectation value of sigma z, well, you get 0 in the particular state. In this state, okay. In either one of these eigenstates of sigma z, so whether you pick the 0 eigenstate or the 1 eigenstate, when you calculate the expectation value of sigma y, you will get 0. And likewise, if you calculate the expectation value of sigma x in either one of these eigenstates, you will get 0. So that is not something that we should be surprised about. Okay. So now the question is that the left hand side of this equation is a product of the uncertainty in sigma z and sigma y, right? And on the right side we have expectation value of sigma x, which is 0 in these two states. So the question is like, how does that make sense? So to see how that makes sense, we have to evaluate the left hand side of that expression, and when we do that, we will see what happens. 1 second. Okay, 1 second, please, don't mind. Okay, so now what we want to do is we want to calculate these quantities, delta sigma x, delta sigma y, and delta sigma z. Okay, and again, the expectation value, these quantities, they depend on which state you're talking about, right? So if you are this delta for any operator, what is this? This is equal to the expectation value of a square, which is a square is the operator a squared minus the square of the expectation value of a. Okay, so now if you look at any one of these operators, let's say you look at sigma x. So there are some properties of these polymatrices. So sigma x looks like this, 1, 1, 1, 0. This is also known as the swap operator, by the way, because what it does is it swaps the two components, alpha and beta. So if you look at sigma x and you take sigma x squared, right? Well, you can multiply it by itself. It's very simple. You can do it like, looking at it, it's the identity. So when I want to calculate the uncertainty in sigma x, okay, it doesn't matter which state I calculate it. I have the expectation value of sigma x squared minus the expectation value of sigma x squared. So now, since sigma x squared is 1 is the identity, this means that the expectation value of sigma x squared is equal to the expectation value of just the identity operator, right? And the expectation value of an operator is what? Again, the state, the operator, and the state. So this means that the expectation value of 1, the identity operator, is the state, the identity, the state, which is just equal to psi, which is equal to the number 1, right? Not the operator 1 or the matrix 1, but the number 1. So then delta sigma x will be equal to root of, right? We have that this is equal to 1 minus expectation value of sigma x squared. Okay. Now you can show the same thing for sigma y and sigma z, because both of these satisfy the same relationship. The square of all three of these operators is 1, or the identity. Okay, so now we can calculate this. So we can take any state. We can take, let's say, psi is equal to alpha 0 plus beta 1. Okay, and we can ask what is the expectation value of sigma x in this state. So sigma x is equal to this expectation value is sigma x. Okay, so the average value of mean value of sigma x. And what is this going to be equal to? This is equal to, so the bra psi can be written as alpha star, beta star, sigma x is 0, 1, 1, 0, and ket psi is alpha beta, right? So you can multiply this. It's again straightforward to see that this becomes alpha star times beta plus alpha beta star. Okay. So this tells you that the expectation value of sigma x, I will write this as sigma x with a bar on top because to make contact with the statistical notion of mean value, is equal to twice the real part of alpha star beta. Okay. In exactly the same way, you can calculate the expectation value of sigma y, and that comes out to be equal to the imaginary part of this expression. And the expectation value of sigma z turns out to be equal to alpha squared minus beta squared. Okay. So this expression you can understand, this alpha squared minus beta squared you can understand easily, all right, because this guy has an angular momentum plus half, or well, eigenvalue plus 1, and this guy has an eigenvalue minus 1. So if both of these components are equal, then what is the total angular momentum? The sigma z angular momentum is 0, right? So if alpha squared is equal to beta squared, expectation value of mean value of sigma z is 0. Okay. Now now we can calculate our expectation value here. Okay, because we have this expression for sigma x. So let's look at some particular choices of this state. Okay, so let's look at, let's say, 0. This means that alpha is equal to 1, beta is equal to 0. And so this means that sigma x, the expectation value of sigma x, is going to be, you can just read it off from this equation. It's going to be 0, right? Because beta is 0. Similarly, expectation value of sigma y will be 0. And expectation value of sigma x, sigma z, will be alpha squared, which is 1, plus 1 in this case. Okay. You can do the same thing for the opposite state. Psi is equal to 1, let's say. So alpha is equal to 0, beta is equal to 1. So sigma x, sigma y, and sigma z. This will be 0, this will be 0, this will be minus 1. Okay, so these are the respective mean values. So then we can ask, what is the uncertainty in these operators? We can ask, what is delta sigma x? So delta sigma x, in the previous equation we had this. So it is root of 1 minus mean value of sigma x squared. So if I calculate delta sigma x in the state 0 or the state 1, right? What is the mean value of sigma x? It's 0. So this means that delta sigma x is equal to 1. Similarly, delta sigma y, the same way, will be equal to 1 minus sigma y mean value squared. And delta sigma z is equal to 1 minus sigma z squared. Now, what is mean value of sigma z squared? Mean value of sigma z squared, because we are looking only at these two states, 0 and 1, the mean value of sigma z in 0 is plus 1, and in the other state it's minus 1. So the square of the mean value in both cases is 1, and that means delta sigma z is equal to 0. And so all of this you have to keep in mind is in the state psi is equal to 0 or 1, right? So what does this tell us? This tells us that in these two states, right? And these two states are what? 0 and 1. These are eigenstates of sigma z, right? So if I make a measurement of an operator, now let's again remember what is the algorithm for measurement. If you measure an operator A on a state psi, system collapses into eigenstate of A, right? And that eigenstate of A is, let's say, phi of A. Okay, never mind. Phi of A, and then the value of the result of the experiment is with a result which is the associated eigenvalue. So let's say lambda A. So if you measure sigma Z, right, and you already are in the state 0 or 1, what happens? Well, the system doesn't have to collapse into anything. It's already in that state, right? On the other hand, when you measure sigma 0, when you measure the expectation value of sigma x or sigma y, and you happen to be in the 0 state, okay, what will happen? To understand this, let's ask what are the eigenstates of sigma x and sigma y, right? Because if I measure sigma x, the system collapses into an eigenstate of sigma x. What is the eigenstate of sigma x? So the eigenstate of sigma x is the eigenstates are, we have worked this out in the previous class. They are these two states, plus state and minus state, where the plus state is 1 by root 2, 0 plus 1, and the minus state is 1 by root 2, 0 minus 1. These are the two eigenstates of sigma x. So when I measure the expectation value of sigma x, what happens? I measure sigma x. What happens? My state, I don't know what my state is to begin with, okay? My state sigma phi collapses into, this is a collapse into plus or minus, right? And result is the eigenvalue. So I get plus 1 or minus 1. These are the two eigenvalues of sigma plus and sigma minus, right? But now we can ask what happens if the initial state, the one that you begin with, is 0. So if it is 0, then notice that 0 state can be written as a superposition of plus and minus. 0 can be written as a superposition of the plus state and the minus state. So if I take the plus state and add the minus state to it, what will happen? This component 1 will cancel out, and I will be left with 1 by root 2 plus 1 by root 2, which is 2 by root 2, which is also 1 by root 2. So again, I should put a 1 by root 2. So the 0 state is again a superposition of plus and minus. So to begin with, my initial state, psi initial, is 0, okay, which is a superposition of the plus state and the minus state. I measure sigma x, right? Now you see that there are two options. The system can collapse into either the plus state, and what is the associated probability? Anybody? Quickly.
Minus 6.
1 by 2.
1 by 2.
1 by 2 with probability 1/2, and the probability for the other state is also 1/2, right? So if you are in the 0 state, right, and you measure the value of sigma x, then there is maximum uncertainty, right? Because the system can go either into the plus state or the minus state. You understand? I hope, are you all following? This is important to understand. So I am taking a measurement of sigma x, right? So the system has to collapse into an eigenstate of sigma x, not an eigenstate of sigma z. So you might think that from all this discussion, in your head, you might only have 0, 1, 0, 1, ket 0 and ket 1. So you might think, well, the system can only be in, when I take a measurement, it can only be in the 0 state or in the 1 state. Am I right? That might be the default thinking, right? But that's not correct. You have to remember the measurement protocol. And what is the measurement protocol? It is this. So the system ends up in a certain state. The state it ends up in has to be an eigenstate of the operator which you choose to measure. This is very important to understand. Okay. Questions?
Sir?
Yeah.
Sir, you said in yesterday's class that when you measure angular momentum in z direction, then angular momentums in x and y direction are either 0 or undefined.
Right. So that's exactly what is happening here. But again, like I said, it depends on the state in which you measure that angular momentum. Okay. So if I am in the 0 state or the 1 state, and who was this? Sorry.
Sir, Deepak.
Deepak. If you were in the 0 state or the 1 state, right, and you measure the expectation value of sigma x and the expectation value of sigma y, what do you get? You get 0. Not undefined. You get 0. Sorry, that was my mistake. And the expectation value of z in that state is +1. Okay?
Okay. Okay.
So then, and we can ask, what is the uncertainty in those respective values? So the uncertainty in sigma x is 1. It's the maximum amount of uncertainty, right?
Yeah.
Because what is the maximum possible eigenvalue of sigma x?
1.
And the minimum possible value?
-1.
So if I say that the uncertainty in sigma x is 1, right? Meaning that whatever value I get, my answer is going to be plus or minus 1. That is the maximum possible uncertainty in my variable, no?
Yeah, correct. Correct.
So when I am in the 0 state and the 1 state, what is the maximum? What is the uncertainty in sigma x and y? It's the maximum possible uncertainty. So I have minimum knowledge about sigma x and sigma y when I am in this state, right? And this is also what the uncertainty principle is a reflection of. So now you can put all of this into, for example, the expression for the uncertainty principle. So this is equal to 1/2 absolute value, expectation value of sigma x, sigma y. Now the right hand side is equal to 1/2 sigma x, sigma y, commutator is equal to 2i sigma z. When I take the absolute value, the I will disappear and I will be left with twice the expectation value of sigma z, 2 will cancel. So delta sigma x, product of these two uncertainties, is greater than or equal to the expectation value of sigma z. And the same way, because of this cyclic permutation in the commutation relationship, you have delta sigma y, delta sigma z is greater than or equal to the mean value of sigma x, delta sigma x, delta sigma z is greater than the mean value of sigma y. Okay. Now, all of this, again, let me emphasize, depends on the state in which you make the measurement. Okay. So again, let us say that our initial state of the system is 0 or 1. Okay. Then let us look at any one of these relationships. Let's look at this relationship. Let us ask what happens here. Now, what is the uncertainty of delta x in either one of these two states? It's a maximum, right? So delta sigma x is 1. The uncertainty in delta sigma y is also 1. What is the mean value of sigma z? Absolute value of mean value of sigma z. In either one of these states, it's also equal to 1. So this is correct. This relationship is true. Then we can ask, well, what about the other guy? What about this guy? Well, delta sigma y is 1. Uncertainty in sigma y is maximum. What is delta sigma z? That is 0. Right? Because when you are in this state, we know the value of what sigma z is going to be. And this is greater than or equal to the mean value of sigma x, absolute value of the mean value of sigma x. What is the mean value of sigma x in either one of these states? We calculated that it's equal to 0. So this is also correct. You can do the same thing for the other two combinations, right? So this relationship is respected for all three combinations of these states. Okay. Now, your homework is the following. Okay, we construct the operator. We write down sigma squared. Okay, and now this is just sigma without any x, y, z. So what is this equal to? This is equal to sigma x squared plus sigma y squared plus sigma z squared. Right? So there are three operators, and I am just taking the square of these three operators, adding them, I get a third operator. So the question is, calculate the expectation value of this operator sigma squared and the uncertainty of this in this operator delta sigma squared. So be careful, this is not delta sigma whole squared, it's delta of sigma squared in an arbitrary state. What is that arbitrary state? Alpha 0 plus beta 1. What happens we are already losing people when alpha is equal to 1, beta is equal to 0, Okay, what happens? Meaning that what can you say about the expectation value of sigma squared and the uncertainty in sigma squared in this specific state? Okay. All right. So this is it for the uncertainty principle of these spin angular momentum operators. Okay. Now the thing is that please work through all of these examples that I've shown you and study them, because like I said, I can ask something about this on the midterm. That is the important tip I was going to give you. Okay, so I have kept my end of the bargain. Now the thing is that I want to continue talking about the thing we started yesterday, which is the relationship between the discrete and continuous representations of quantum states. Okay, so what I told you is that if you have a function f of x and it's defined on some domain, some subset of the real number line, right? So it's a function from some segment of the real line AB to R, meaning that it gives you a value of the real number for every point on this line. Then these functions, they form a vector space, because if I take any two functions and I take a linear combination of these two functions, this also gives me a function. So I'm using this notation that the set of all these functions is written as this fancy capital F. So these are vectors. In what sense are they vectors? They are vectors, well, because if I take the sum of any two functions, I get a function. I can define an inner product of these objects. What is the inner product? I can write down the inner product of two functions f1 and f2. And now remember that this can either be R, it can also be C. I can have real functions or complex functions. So when I'm writing this notation, then it's understood that we are talking about complex functions. So we have f1x, f2x, dx. And this looks exactly like the inner product of two vectors, ui, u, and v. The only difference is that here the index is I, and here the index is x. That is the only difference. Okay. Now, as an example, we can talk about the particle in a box. Okay. So the particle in a box, if you remember, the solution of the particle in a box looks like this. Root of 2 by L cosine n pi x by L. And so this has a subscript psi of nx. Okay. Now, I know that some of you might not remember what this is, or you might say that, well, how can I introduce this without showing you the Schrodinger equation and all that? But please keep in mind that technically this is an MSc level course, and the expectation is that, well, you remember or you have revised these things from your previous course. If you have not, don't worry, you can go back and do so, right? At this point, you don't need to worry about how you get this. I'm just going to use this to show you something else. So first of all, let me ask, what is the inner product of two such states, psi m and psi n? Okay. So the inner product of two states, like I said, is psi m x, psi n x dx. Okay. So your next homework problem, your second homework problem, and I've already given you some other homework problems regarding the commutators of xy in the previous class. We just lost one more person, or we gained one more person, I don't know, something. This homework problem is calculate this expression, show that it is equal to delta mn, where delta is the Kronecker delta. So what does this tell us? Okay, this tells us that when we do this, it tells us that these two states, psi m and psi n, they are orthogonal. It also tells us that they are normalized, right? Because if I take psi m, sorry, did I use psi m and psi m, I get 1, right? So what is the so these states, right? These states are vectors. They form a complete basis of our Hilbert space. They form a complete basis of our Hilbert space where m goes from 1 to infinity. And so this is an infinite dimensional vector space, right? So it seems a little bit scary. You're not accustomed to seeing infinite dimensional things, but there is no reason to be scared. They behave almost the same way as finite dimensional vector spaces, right? If you have any state phi in this Hilbert space, you can write phi as a linear superposition of our states, of these states. So you can write it as alpha m psi m. Only difference is that now m goes from 1 to infinity. Okay. So you have a third homework problem from this. Plot the probability density. Now, what is the probability density? It's equal to phi x squared for the states phi is equal to 1 by root 2 psi 1, 1 by root 2 psi 2, and for the state 1 by root 2 psi 1 1 by root 2 psi 2 with a minus sign. Okay. So these are the two questions. Shashwat is asking, the Hilbert space is in question is countably infinite. That's right. This is countably infinite, right? Because you can count the elements of that set. And an example of an uncountably infinite Hilbert space, as he's asking, is also very easy. An uncountably infinite Hilbert space is the Hilbert space whose basis elements are the position eigenstates of the position operator. So here, if you have any state psi, you would write it as a superposition of these position states. And that superposition will look like this. And so in this expression, there is an uncountably infinite number of components. Okay. So this is what I meant when I said that psi of x is a component, right? So this ket psi is your actual state. Psi of x is the component of this state psi at the point x. And what is this ket x? This ket x is the eigenstate of the position operator. That means I have some position operator. When it acts on this state, I get an eigenstate, which is just the position x. Okay. So I'll leave it here for today. And you guys can go ahead and ask whatever questions you have. And please remember that I have given you some homework problems, and they are due before the midsem. Okay. Okay, questions? Any questions? No questions? No questions? Okay, well, I will, in that case, I will stop the live recording, and then you can ask me questions without fear of being recorded online. Okay. Let me see if there is any question on the YouTube chat. Karthik, Akash, and Rohit are watching. If they have questions, you please ask me on Telegram. I can answer them.